what I hope to accomplish in Chemistry 52 is to continue the coverage began in Chemistry 51. You have very good preparation from Professor Jacoby about the basic understanding of organic chemistry. The laboratory, of course, will continue your techniques in the laboratory. And then the main difference between 51 and 52 is that I like to introduce special topics, 5 special topics. And the idea here I have is to expose you to the relevance and how pervasive organic chemistry is in our lives. And many of you will become doctors, I know, and you'll be dealing with some of these special topics that I'll talk about in just a minute. To complement that, I also like to introduce natural products. That's my area of research, in part. The fact that organic chemicals are ubiquitous in nature, and they're, in some cases, identical to synthetic compounds. Synthetic pesticides, turns out, are made by sponges, the same compound, as you'll see. So the special topics, the first of which is chemical evolution. We'll talk about that today. I thought this was a good topic because it actually covers, as you'll see, all of the compound classes, the functional groups that you had in 51 and that you will have in Chem 52. And these are present, as you'll see, in outer space, in our galaxy. Then we'll talk about insect pheromones and chemical defense secretions, so-called allomones. And these are compounds, in fact, in insects, obviously, and in other animals, mainly insects, that are similar to the compounds we'll encounter in chapter 18, 19, and 17. Alkenes that you had last term in chapter 7 and 8. We'll see aldehydes and ketones, alcohols. All of these are produced by insects as pheromones, and we'll get into that in about 2 weeks. Then we'll talk about pesticides, most of which are organic compounds. Unfortunately, the compound that killed the 4 children in Texas a couple of days ago is a pesticide byproduct, if you will, but not an organic compound. That's actually phosphine. Very, very toxic compound that unfortunately killed those kids in Texas. And as part 2 of that special topic, we'll talk about herbicides and dioxin, the compounds used in Vietnam. And these are still posing major problems in the environment. Then we'll talk about compounds that cause cancer. This is a long special topic. I think this will be of great interest to you guys going to medical school, and more than half of you will be going to medical school, I'm sure, fingers crossed. And we'll see how organic chemistry plays a major role in how chemicals cause cancer, both with regard to the SN1 reaction you had last term and the SN2 reaction. Both of these are involved in the mechanisms of how chemicals cause cancer. Then finally, we'll talk about chemical warfare, and this is also of interest if you're going to medical school. It involves an enzyme, nerve gas at least, involves an enzyme. Extremely toxic compounds used, as you know, in the Middle East. Okay, I want to get into the special topics now. And again, special topic number 1 deals with chemical evolution, its possible origin of life on this planet. And this began in 1924. Yeah, these slides are in the syllabus, with maybe 1 or 2 exceptions. A Russian biochemist, Oparin, proposed that, in fact, methane, water, ammonia, and hydrogen, molecules he thought that might be on prebiotic Earth. You might not have all of the slides, but yeah, it begins right there, yeah. What page number is that, by the way? Yeah, page 9. And he proposed that these molecules, which might have been present on prebiotic Earth, would account for carbon, hydrogen, oxygen, and nitrogen, which are the 4 atoms necessary for life. And of course, he was laughed out of Russia, but he proposed that a suitable energy source, if indeed these molecules were present on prebiotic Earth, would lead, in fact, to life. Now, nothing much happened until 1968. And this was the development of the radio telescope, examples of which are around the world, including in this country, that allowed the detection of organic molecules and other molecules based on their microwave radiation. And this has to do with infrared. You can actually detect these, much like taking the IR spectrum that you did last term. And here is a typical example of the radio telescope. And people then began to look at emissions from distant parts of our galaxy, within the Milky Way galaxy. And you have these gas clouds that, as it turns out, as you'll see, contain an amazing array of organic and other molecules. You can see these gas clouds here. What the heck? Peter Jacobi did that, I'm sure. Son of a gun. Anyway, I talked to him. And now, of course, the Hubble telescope has gone beyond the Milky Way galaxy and is able to get photographs, amazingly beautiful photographs, of these other galaxies that are very far away, in fact. Although that one's still within the Milky Way. Just amazing. And all of these, galaxies, of course, contain billions of stars, much like the Milky Way, and there are billions of galaxies. I mean, it's truly mind-boggling. I mean, this is really a long ways away. A light year is, 4 trillion miles or something like that? I forget the exact distance of a single light year. Okay, so before 1968, some other fragments were identified using other techniques, really of no consequence, not organic molecules. But in 1968, it was detected ammonia and water, two of the molecules that Operin proposed were present on prebiotic Earth and could conspire then with other molecules to make the molecules of life. 1969, formaldehyde, the first organic compound, was discovered. We're going to talk about aldehydes a lot, and you probably have already to some extent in chapter 19. 1970, methanol, methyl alcohol, wood alcohol was detected, cyanoacetylene, and formic acid. This is the venom of some ant species. The simplest carboxylic acid we'll talk about in chapter 20. 1971 was a good year, as you can see. All kinds of compounds. Here's a sulfur ketone, if you will, and nitrile, the CN triple bond, and amide. This is formamide, the simplest amide. And of course, all of our protein is made up of amide bonds. This is the simplest amide bond. Acetaldehyde, the oxidation product of ethanol, was detected as well. And hydrogen cyanide, the gas that killed upwards of 6 million people in Nazi Germany, was detected. Now this one, unfortunately, did not make it to the syllabus. Again, it's on Canvas. Imines, we'll talk about imines, the condensation product between ammonia and formaldehyde. A giant cloud of that imine was detected in deep space. Ethanol, ethyl alcohol, in 1974 was detected. Protonated nitrogen. This is the protonated form of carbon monoxide, and this, in fact, as you'll see, the Friedel-Crafts acylation we're going to talk about. Some of you will attempt to generate that. Unfortunately, in order to make an aldehyde on a benzene ring, as you'll see, unfortunately, this can only be detected in deep space, can't be used here. It's unstable. Water was detected outside of our galaxy for the first time in 1977, and then a lot of these polyacetylenes. Glycine, which is the simplest amino acid in everything, in all of our protein. You ate some glycine today for sure if you had any protein for breakfast or lunch. Sodium cyanide, laughing gas in 1994 was detected. Here is a simple ether. We talked a little bit about it last term. We'll talk more about that in chapter 17. And amine, methylamine. Acetic acid, the acid in vinegar, was detected. Acetone, the compound you use in the laboratory, was detected in 1997. The simplest epoxide, I think you encountered in chapter 8. Talk more about that. And here's an example. This is acetaldehyde, but the tautomeric form. And normally that's not stable, but in deep space where the concentration of these molecules is typically 1 molecule per mil, very dilute. So the molecules never have a chance to collide with anything. They're so dilute. And that's why this turns out to be stable as the enol form, not the tautomeric aldehyde form, as we'll see. Okay, just some more evidence about this. Again, propene, the first alkene to be detected in deep space. And buckyball, C60, this third or fourth form of pure carbon. And this is now turning up everywhere. It was first detected, as you can see, in 1985, even though it's been around for billions of years, probably. And it's named after this guy who actually invented the dome in Montreal. It's been found, as you can see, more recently. Okay, so these molecules are there. But what about molecules closer to Earth? Now, all of these things were detected within our galaxy, but a long ways outside of our solar system. Well, here are some molecules that have been detected. Methane, ammonia, ethane, acetylene detected around the planets Saturn and Jupiter, in the gases surrounding the planets, in some cases on the planets. Titan, this moon, contains a variety of compounds, including benzene, which we'll encounter today, later, if we have time. Mars, there's a giant pool, lake of liquid methane, maybe more than one. A recent discovery, as you can see a few years ago, chlorobenzene, we're going to make this on the blackboard in just a minute, was detected on Mars, along with the dichloropropane. Just amazing compounds that are found outside of McMurray, obviously, outside of this course. They're also found in comets. Here's a famous comet, actually Halley's comet, I think, or the Hale-Bopp comet, different. Ammonia, water, hydrogen cyanide, formaldehyde, all are streaming off of this comet as it travels around our solar system. More recently, it was the Russians identified this comet, and in fact, we were able to land a probe on this comet, which is only about 3 miles in diameter, and the probe detected acetone on this comet, this simple aldehyde, propanal, acid amide, again, a simple amide that has a peptide bond that holds all of our skin together, and this isocyanate. It's the compound that killed about 5,000 people in Bhopal, India, some time ago, in this chemical accident we'll talk about when we talk about pesticides. Now, the probe actually landed up here initially, but apparently fell, rolled down, and wound up right about here, I think. Here's another comet Lovejoy, found to contain ethanol, the simplest sugar. We talk about carbohydrates in chapter 25. Antifreeze, ethylene glycol, which is actually very suited for these cold regions of space, was found, and again, formamide. And we're going to talk about all of these kinds of compounds. These are everywhere, not just in McMurray. More compound. This compound, discovered just last year, in fact, is the first example of a chiral molecule with a chiral center. It's probably racemic. They don't know for sure, but it's the first time a carbon atom that is chiral, as you learned about last term, was detected in interstellar space. Again, Lovejoy is exuding lots of alcohol, as you can see, just tremendous quantity of alcohol disappearing into space, obviously. Okay, so the molecules are there, at least in outer space. On Earth, of course, we don't know necessarily, on prebiotic Earth at least. What about the energy sources? Well, there's lots of energy thought to be present on prebiotic Earth, going back millions of years, that could engage the simple molecules, methane, ammonia, water, hydrogen, to form more complicated molecules. The sun, a lot of energy. The ultraviolet radiation also from the sun, of course. The action of lightning bolts, which occur around our planet all the time. Volcanoes, we had a big eruption on the big island of Hawaii just yesterday, I guess. The impact of meteorites, and some other possible sources as well. And I'll just show you some of these sources that you all know about, I'm sure. And volcanoes. And here, one proposal recently made that, in fact, meteorites, which are impacting Earth all the time, are actually bringing forth these molecules, because we saw those molecules in the meteorites, Lovejoy, Hale-Bopp, and others, that they're actually seeding Earth with these molecules. And again, meteorites are hitting all the time. Here's one that landed in Oregon in 1911. And this guy was really lucky, really lucky. Okay, so we have the molecules, we have the energy sources. Was Oprah correct? Well, in 1953, Stanley Miller, a graduate student in Chicago, had the idea, knew about Oprah, and let's take those four gases I showed you on the first slide, subject them to a lightning bolt, and see what happens. Here's the lightning bolt, basically, and he got out 4 amino acids that are in everything we eat, that is protein. Glycine, alanine, aspartic acid, glutamic acid. And actually, if you read in the syllabus, I think starting on page 17 or so, right after 16, you can read about his experiment, and his samples from 1953 were reinvestigated, and they were found to contain many more amino acids, and also proteins, little tiny proteins, peptoids, or peptides. Just an amazing, I mean, these are complicated compared to these simple gases. And then people have broken this down. If you take methane and water, subject them to a lightning bolt, you get formaldehyde. Methane and ammonia gives hydrogen cyanide. This is the gas that killed all of those people used in this country, San Quentin, when it had the gas chamber, was used hydrogen cyanide. And then if you mix ammonia and water with these guys, you get glycine. And you can do this in a laboratory. Just amazingly simple chemistry. And here's his apparatus. And so he put the gases here. The electric spark came out here, and then the compounds fell down into the trap and were identified. Not just glycine, but you can take ethane just by itself, subject it to an energy source, you get phenylacetylene. And as you learned in the alkynes chapter, I forget, maybe chapter 8 or so, or 9, you in fact can hydrate alkynes, and this gives phenylacetaldehyde. As we're going to see later in this course, near the end, if you take an aldehyde, ammonia, and hydrogen cyanide, you make amino acids. And this gives phenylalanine, the Thanksgiving Day amino acid that you guys probably had a few weeks ago. Also, the amino acid in NutraSweet, which is a dipeptide, is phenylalanine. Now what about, okay, we have the amino acids, and those are the monomers of proteins, of course. What about nucleic acids, our DNA and RNA? Well, it turns out you can take this amazing molecule, very toxic hydrogen cyanide, subject it to an energy source. 5 of these molecules get together and form adenine. Adenine's in all of you and me, our DNA and RNA. It's one of the 4 or 5 nucleic acid bases. Just some amazing chemistry. And here's the mechanism. You don't have to know this. We're going to be talking about similar kinds of reactions, but you can see how 5 cyanides can get together and form adenine. You can actually write a chemical mechanism, and you'll be able to do this, I think, by the end of this term. Okay, what about the other nucleic acids? There are 5, of course, that are in all of us. If you take urea, which Dr. Jacoby talked about, I'm sure, the first organic compound to be synthesized a long time ago. It's in our urine, simple compound. And treat it with the apple acid, malic acid. Just heat those together, you get uracil. And uracil is the amino acid, or the nucleic acid in our RNA. And if you subject that to formaldehyde and hydrazine, you methylate it, And you get thymine, which is the other nucleic acid in DNA that we'll talk about at the very end of the course. Well, what about other compounds? So we have amino acids, nucleic acids. Well, there are other kinds of compounds that are of interest that we need. Vitamin B3 that we need for good health is shown here. It turns out you can take methane and water, and you get this compound along with a myriad of other compounds we've already talked about. You can take methane and nitrogen, and you get this cyanoacetylene. You can hydrate this. This mechanism we'll see in a later chapter, and this mechanism we'll see in a later chapter and on the next slide. And this gives the cyanopyridine. Now, pyridine is a benzene ring with one nitrogen replacing a CH group. You may have encountered that last term. You can hydrolyze the CN triple bond and make, in fact, vitamin B3 under very simple conditions. Now, these mechanisms, of course, you don't have to know. Nobody knows exactly how these reactions occur. These mechanisms shown here, we will have later in the term. Very simple chemistry we'll have in later chapters where the ammonia can attack this carbon of this alkyne aldehyde, and it can attack the aldehyde in this cyanoacetaldehyde, and aldol condensation here. And all of these compounds occur in you and me all the time because they're in biochemistry, the biochemical reactions. And this then, after hydrolysis, will give vitamin B3. Started with a lightning bolt, as you can see. Okay, there are lots of other compounds. What makes your blood red is this molecule with an iron in the middle. It turns out you can take perol, which is like benzene, only a 5-membered ring. You may have had this at the end of 51, I'm not sure, with formaldehyde, an energy source, and you make this. If you're a purist, what you would do is just to start with methane, ammonia, and water. And the yield is lower, certainly, but it also makes this. And this is the basic unit in all of your hemoglobin, chlorophyll, and some other things like vitamin B12, as you can see. Just amazing chemistry thought to occur on prebiotic Earth. What about sugars? As you know, nucleic acids are DNA, and RNA is a nucleic acid base connected with a sugar phosphate backbone. And again, we'll encounter that at the very end of the term in chapter 23, I think. Well, formaldehyde, we've seen before, under the same energy conditions can keep going and form ribose, which is the sugar in all of our RNA, and deoxyribose, the sugar in our DNA. Very simple chemistry, and you can actually write a mechanism for this. In fact, formaldehyde also undergoes polymerization. And this is polyoxymethylene, and this was found in Halley's Comet, the polymer of formaldehyde. So we have amino acids, it turns out, under simple heating can polymerize and form proteins and perhaps enzymes, and nucleic acids then can polymerize as well and form DNA and RNA. But there's a big leap going from all these molecules we've just made on prebiotic Earth, presumably, to living cells. So the final slide shows a very interesting observation, a property of proteinoids, which are basically peptides made by polymerizing amino acids. If they get long enough, it turns out they form a sphere, a microsphere. Then they don't keep growing, except they form buds, and the buds will keep growing until they reach a certain size, and then they divide, much like living cells. Very interesting phenomenon, a physical phenomenon called the formation of microspheres. And the idea that some people have is that the molecules that we just made using these tremendous energy sources would be in the microspheres and be protected from the environment. So the energy sources that made the molecules we just talked about would be protected within the microspheres. Very interesting observations. Okay, any questions about special topic number 1? Again, one thing I didn't say is sample exams are on Canvas, and you can have a look at sample exam number 1 from last year to see how I cover the special topics on the exams. It's never worth a lot of points, and the questions are very general. If you paid attention today, I'm sure you'd get 100% on the question that would appear on your exam in a couple of weeks. I think that's on the 23rd, our first exam. Okay, that's the end of the special topic, and I do have a few more slides. Okay, chapter 16 is our first regular topic. Deals with benzene chemistry. Again, one of the 5 most important reactions in all of organic chemistry, aromatic electrophilic substitution. And with each topic, I like to include examples of where these compounds, the different functional groups, occur in nature. And with benzene, gasoline is a good source of aromatic hydrocarbons, including benzene, not too much, but a little bit. Toluene is methylbenzene. And these are molecules you should probably memorize the name, because on the board I'll say toluene, not methylbenzene. So you should probably learn at least toluene and xylene. Xylene is a dimethylbenzene. And of course, as we'll see today or Friday, you can have 3 different isomers of dimethylbenzene. They can be 1,4 called para, 1,2 dimethylbenzene, orthoxylene, or 1,3 would be metaxylene. But lots of other compounds. If you went hiking in the woods this summer, I hope you didn't get bit by a tick, but if you did, the female tick, if it was secreting this compound. That's the sex pheromone of 14 species of tick, 2,6-dichlorophenol. And here's a compound that's in badly made wine. Lots of marine worms and sponges make these compounds. Plant materials, all of these have benzene rings. In special topic number 4, chemical carcinogenesis, we'll talk about benzpyrene. This very potent carcinogen forms when you burn anything that contains carbon. If it's not burned completely to CO2 and water, you form this. And this causes bladder cancer in man. This is in diesel exhaust. So lots of natural examples. Naphthalene is also found in lots of different places. It's used by termites to repel ants. Nitro compounds are fairly rare in nature. Here are a few I wanted to mention. And we'll talk about how you make nitrobenzene probably today, if not Friday. And here's a compound just a couple of years ago was discovered from a fungus growing on a sponge in the Antarctic. Very interesting nitro compound. Okay, these are the reactions you learn in Chemistry 51. They're still valid here, but they don't apply to benzene. As you know, alkenes can be hydrated, hydroboration to make the epoxide, or the alcohol. Yeah, actually, alcohol here, sorry. Peracid makes the epoxide. You can hydrogenate alkenes very easily, hydrogen and palladium. Again, this is on Canvas. If it's not in the syllabus, I don't think it is, actually. You can ozonize alkenes, as you know, to cleave to a dicarbonyl compound, add acid, HBr, for example, bromination, electrophilic addition to give the trans product by way of the bromonium ion, you may recall. None of these reactions work with benzene. Benzene, because of its extreme stability, that you learned about last term, is impervious to this chemistry. We can make, as you'll see, bromobenzene, but not just by adding HBr. None of these conditions will do anything to the benzene. It's so stable, as you learned in chapter 15. We typically draw benzene this way because it's easy to show how it reacts, as you'll see on the blackboard, even though we know that all 6 carbon-carbon bonds are of the same length. And it's an aromatic system, very difficult to break that 6 pi electron aromaticity. So It's often drawn like this in books, but if you draw that, then it's hard to show how it does react under special conditions. So we're always going to draw it this way, as you'll see, keeping in mind it's really a resonance hybrid of these two extreme forms. Again, this is all on canvas. So here's the electron clouds, benzene. It does react as a nucleophile in the most important reaction of benzene, and this will play a role in how benzene causes cancer, causes leukemia, depending on the dose. Very important reaction, electrophilic substitution, where benzene is the nucleophile and it's attacked, can be attacked by a very powerful electrophile. So we're going to focus on that reaction first. And this then sort of summarizes, I'm going to do this on the blackboard later, but you can imagine some electrophile attacking the benzene. It can't be just any old electrophile. It has to be a very special, powerful electrophile with a capital E. And then you get the carbocation. Now this first step is reminiscent of when an electrophile attacked an alkene that you had last term in chapter 7 and chapter 8. Same idea. The difference is now you have a carbocation that's resonance stabilized by the other two double bonds. And that's called a sigma complex. So you can write the charge here and then up here. And in fact, it is delocalized around the ring. Now, oftentimes you'll see some people writing this way. This is probably not to be recommended. This way, and that illustrates the fact that you have two double bonds, one positive charge over the 5 sp2 carbons. It's better, I think, to draw all three of these out if I ask you on the first exam for a mechanism. The other way that I have seen is a dotted line. And what they mean is that's a resonance structure of all three of these together. But I would stick to this form. And again, we'll do more of this on the blackboard. So what happens now, in contrast to the addition of an electrophile to an alkene, with an alkene, like if you add HBr to cyclohexene, as we did a few slides ago, the bromide attacks and you get bromocyclohexane. But here, it's a little bit different. Here, in fact, the base, and this might be anything as you'll see, simply pulls off the proton and reestablishes the double bond. The driving force, of course, is the formation of the benzene ring back again. That's the driving force. That's why you never see, at least with benzene, you never see addition of the electrophile. You see substitution. Addition would correspond to what you had last term, but in fact here you just see substitution. That product is much more stable. The transition state leading to that product is more favorable than leading to addition. Okay, any questions about that? Okay, that concludes the slides for today.